Assalamu alaikum. Welcome to my channel, Muhammad Asif Shahzad, Muhammad Asif Math Corner. In our last video, we discussed about the main definition of group theory, and we discussed the four main properties which prove that a non-empty set is a group. And those four main properties are: first was closure law, that the non-empty set we discussing about, which we are going to prove that it is either group or not. So we check the first property was closure law, either that non-empty set is closed or not. The second was associative law, and the third was identity. Identity is a unique element should exist in that non-empty set, and the last one was inverses. The inverse of each element should exist in that non-empty set. So today we will discuss about some examples of group theory, which non-empty sets are groups and which are not groups. So let's start. The first set is set of natural numbers. We are going to check that either the natural numbers are group or not. So we have to one by one check the four properties we discussed in our last lecture. The first property was the closure law, and in closure law we take any two elements from that set. Uh, Here we take 2 and 3. Here we take 2 and 3, and we are going to check that by addition law 2 plus 3 is equal to 5, and 5 belongs to natural number. Here 2 belongs to natural number, 3 belongs to natural number. 2 plus 3 is equal to 5, and 5 belongs to natural number. This proves that the closure law holds with respect to addition. This means that this set of natural number is closed with respect to addition. The multiplication law with respect to multiplication as well. It is also the multiplicative law also hold, the closure law with respect to multiplication also hold in natural numbers. Now we check the second property, that is associative law, and associative law, in associative law we take three elements 2, 3 and 4 from the natural numbers and apply the associative law. 2 plus 3 plus 4 is equal to 2 plus 3 plus 4. 3 plus 4 is equal to 7 plus 2, and 5 plus 4, that is equal to 9 is equal to 9. This shows that associative law also hold in commonly all the sets associative law hold with respect to addition and multiplication. This means that the set of natural number is semi-group. We know that if closure law hold, then that set is groupoid, and if also associative law hold, then the non-empty set is called semi-group. Now we check some other properties. The third property is identity element. Here is the problem in this set. We know that the set of natural number does not contain 0. It starts from 1 to 3. So we know that 0 is additive identity. So additive element is absent. Additive element is absent in this set. That's why set of natural number is not a group. Set of natural number is not a group because identity element does not exist in it. Like that, similarly, the set of whole numbers which start from 0, 1 to 3, the identity element with respect to addition is exist, but inverses does not exist. We know that the inverse of 2 is minus 2, and inverse of 1 is minus 1, plus 1 is minus 1 with respect to addition. So the inverses does not exist. That's why the set of whole number is also not a group. Let's check some more sets. Set of integers. We know that set of integers start from 0, and in this set plus minus both elements exist. Plus 1 is also exist, minus 1 is also exist. So that's why about 0 identity element is also exist. Plus 1 and minus 1 means that the plus 1, the inverse of plus 1 is minus 1. So both inverses also exist of each element. That's why the four properties, closure law, associative law, identity, inverses, four hold. That's why this the set of integer is group with respect to addition but not multiplication, because we know that the multiplicative inverse of 2 is 1 by 2. So 1 by 2 is not contained in set of integer. That's why the multiplicative inverses does not exist. That's why it is not a group with respect to multiplication, but it is the group with respect to addition. So set of integer is a group with respect to addition. Let's check the next group. Our next group is set of rational numbers. Rational numbers are those which we can write in p by q form, where p and q belongs to integers and integers, and q does not equal to 0. Q should not be equal to 0. If in the denominator there is 0, then we find the infinite, which is not which is not a value, which is not a valid value. So the set of natural number is an abelian group with respect to addition, because it fulfills all the four properties. As we read before that, the closure law hold in rational numbers, because z integers contain in rational numbers. If the z integers is group with respect to addition, then the rational numbers are also group with respect to addition. And with respect to multiplication as well, because here is p by q mean that if 2 is there, then 1 by 2 is also there in set of rational numbers. That's why the multiplicative inverses are also exist, and commutative law also hold. That's why it is called an abelian group. And also an abelian group with respect to multiplication except 0. In multiplication there is a condition except 0. Except 0 means that we know that 0 does not has its inverse. 0 has no inverse. That's why we write always with respect to multiplication that except 0 it is a group with respect to multiplication, because 0 has no multiplicative inverse. Let's check another set of real numbers. Set of real numbers. Set of real numbers is equal to rational number and union of rational number and irrational number, where q is q is a rational number and q is a rational number and q prime is an irrational number. Set of real number is also an abelian group with respect to multiplication and addition as well, because as we read earlier that rational numbers are set of are group with respect to addition and multiplication, and as that the rational numbers contain in real numbers, that's why the real numbers are also set or group with respect to addition and multiplication. Let's check set of complex numbers. Complex numbers are in iota form, we know that, and where a and b belongs to real numbers, a and b belongs to real numbers, and iota belong to imaginary number. Do you know that In 18th century, Sir Euler, the Swiss mathematician, introduced the number iota, which is an imaginary. He said that the under square root minus 2 minus 5 are pure imaginary numbers. From there, the iota comes, and iota is called an imaginary number. The set of complex number is an abelian group with respect to addition and multiplication, because we know that the set of real numbers is a subset of set of complex numbers. So if the set of real number is a group with respect to multiplication, so set of complex number is also group with respect to multiplication and addition. Let's check our last set of we are discussing about today. So this is the set of matrices. Matrices, you know that all invertible matrix makes groups. Why invertible? We know that invertible matrices has their inverses, while non-invertible matrix does not exist their inverses. That's why they that do not make groups. So here is a condition that there are two conditions in matrices. One, the matrix should be invertible, and in second, the but a billion but not a billion. Second condition is not a billion because commutative law does not hold. We know that AB is not equal to BA in common matrices. In matrix, if we multiply two matrices A and B and change its order B and A, the answer is different. That's why commutative law does not hold. That's why abelian group does not exist in these matrices. So uh, in non-invertible matrices does not make the group because inverse does not exist. So the singular matrix does not make groups. Singular matrices are those which are non-invertible. The invertible means those matrices which have their inverses. All non-singular matrices does not make group. So here this was our today's lecture. In in our next lecture we will discuss about some general examples of groups that make the group. Please subscribe my channel if you like it.